Hey, good morning, guys. Give everybody a few minutes to kind of hop in here. We'll get going here in just a second. All right, let's go ahead and get going, guys. Good afternoon. I hope you guys are doing extremely well. Let me do a quick audio check. If you can hear me, whoa, and you can see me a little bit weird. Let me adjust that a little bit. If you can hear me and see me, give me a thumbs up in the chat box. All right, there we go. Much better. If you can hear me uh, and see me, give me a thumbs up in the chat box, please. All right, cool, very good. Looks like we have Ben Morgan and Alex today. Some may join a little bit later. I'm not 100% sure. They may have partied too hard last night at the driving around in circles at the school. Not 100% sure, but hopefully they can join us. So looking at number 28 classwork today. But before we go to 28 classwork, let's review 27 homework. Okay. You have the answers. So, I mean, me showing you the my answers probably won't do much. If you don't know where the answers are, they're under files in Canvas. So you can jump in there and you can see that. You can see all the answers here. I'm not going to read them verbatim, like I said, because you have them, and I assume you've checked if you knew that file was there, but if not, now you know. So you can look at this here, go on there. But any questions of you guys of any problems? Any questions of you three? Morgan has no questions. Alex, Ben, any questions? I can kind of show you mine so just in case you want to see if you were to pause and just look at it. Alex is good. Backside, you guys understood all this and well? All right. hey, if you guys don't have any questions, yeah, I agree, Morgan. It is. I think it's pretty straightforward. So not too much gray area there, but just making sure we all got the algebra going and everything. If you guys don't have any questions, I'm cool with that. Let's jump to number 28 classwork, the accumulation function. Okay, the accumulation function. Now that we understand that the concept of a definite integral is nothing more than an area, let us consider a very special type of problem. Suppose we have the function f of x equals 2. We know that this is a horizontal line, as this figure here shown on the right. Note, realize that the equation of the graph f of x equals 2 is the same as f of t equals 2 or f of k equals 2. Whether we use x, t, k, or any other variable, it doesn't matter. The graph is still a horizontal line. We're used to using x, but we will see that there's a good reason that we will occasionally use another variable. Let me kind of take me out of the way a lot. Sorry. Consider the expression, the definite integral f of t d of t. This is a function of x. It represents the area under the f of t curve shown above here, shown right here, starting at t equals 0 and ending at t equals x, some number. So as x changes, the definite integral from 0 to x f of t d of t changes as well. So let's complete this chart right here. All right, it's x and then the definite integral of f of t d of t based on this graph right up here, guys. Okay, so and you'll see that what we're saying is it's better to use t here instead of x, because if you have a f of x dx here and then an x up here, you're thinking like, man, where in the world do I put the x? So, but in this right here, that's why with this definite integral, in some cases, especially with what we're talking about today, the accumulation function, you're going to always see a t here, f of t d of t. So the x is the upper limit of the integral. So from 0 to x, what is the area from 0 to 0? Plug the first 0 into that x there. What is the area of f of t from 0 to 0? And we know that is just simply 0. All right. What is the area of f of t from 0 to 1? Plug x into the upper limit 1. So that's 0 to 1 right here. And that goes, it has a height of 2, so that would be an area of 2. 2 has an area of, think about right here going up, that would have an area of 1, 2, 3, 4. If we can thought about this as just, x, y, each one's a block. So 4. When it is 3, that would be 1, 2, 3, 4, 5, 6. When it's 4, that would be 8. And when it is 5, that would be 10. Okay? Hey, no issues, Carter. So, it should be apparent that as x gets larger, the definite integral of 0 to x, f of t dt increases as well. We are accumulating area. And we call the expression, the definite integral from 0 to x f of t d of t, the accumulation function. It should be apparent why we use f of t equals 2 rather than f of x equals 2. Because look at this right here. Look how nasty. Just think about how weird this is. It's like the definite integral from 0 to x, f of x, d of x. And that's what I was saying up here, like 0. Where do you put your 0 into f of x, or do you put it into x here? Or or what do you do? So it can be a little bit confusing there. Okay, so that's why you will see this format, f of t is equal to 2. All right, so to the right is the function f of x equals 2x, right here on this graph. And Carter, you haven't missed anything. Obviously, you go back and kind of watch the beginning of it just a little bit, but we hadn't got into anything crazy. Only thing is just we were just calculating the definite integral from 0 to x for this graph right here, and that's where that graph comes from. So, look, starting here. To the right is the function f of x equals 2x. Let's calculate the value of the accumulation function from x equals 0 to x equals 4. So from 0 to 4, we're going to be plugging the x into the upper limit to find f of t, the area underneath those values. So when x is 0, that should be pretty obvious. When x is 0, when you have 0 and 0 here, this is just going to be simply 0. When you go from 0 to 1, you should see from 0 to 1, that's going up 2, guys. So notice that that's going up by 2s. This is going over by 1. So it's a triangle that's a 2 by 1. So that should take us to 1. 1/2 base times height. So 1/2, 2 times 1 is 2, times 1/2 is 1. And then what's the area underneath the line from 0 to 2? Well, that would be a 4 by 2. 4 this way. It has a height of 4 and a length of 2. 4 times 2 is 8. Half of 8 would be 4. Going over 3. 3 would be a 6 by 3 triangle, which is 18. Half of 18 is 9. And going over 4 would be going up 8. 8 by 4 is a 32. Half of that is 16. So now plot those values on the same graph. Let's plot these values, okay? So this is the area, okay, under this curve right here, or under this line. This is the area. This is the accumulating area, the accumulation function of f of x equals 2x, okay? So let's plot those points. We got 0, 0. We got 1, 1. We got 2, 4. We got 3, 9. We have 4, 16. And then connect them with a smooth curve. This curve should be familiar to you. What is it? Someone type it into the chat box. What is this curve right here? Looks a little funky because the y-axis is going up by 2s, but you should be able to see it just by the xy coordinates. Anybody know what that is? 0, 0, 1, 1, 2, 4, 3, 9. Think about this curve. If we kept going this way, it looks something like this. Crickets in the room, in the virtual room, I guess. Yeah, very good. Okay, yeah, there we go. X squared. Very good. So these coordinates right here produce x squared. So, thanks a lot, Morgan, for not paying attention. That's all I need you to do right now is pay attention, and you weren't doing it. I appreciate it. So, now let's take the derivative of the function. So, the derivative of this right here. Well, we just found out that this right here is x squared. So what's the derivative of the definite integral of f of t right here? Well, it would be 2x. So this leads us to a very, very important result, and that's this result right here. The derivative of a definite integral from 0 to x f of t in terms of t is equal to f of x. Now, we will study this formula in greater detail later in the course. I doubt we'll get into too much later detail, but we will in the next couple chapters. You're going to start seeing it, and we only have 2 chapters left. But what this says is that the slope of the tangent line to the accumulation of a function is the function itself. Now, some of you may have got that, but that kind of the wording of it's a little bit unique. Okay. So think about it this way. If we start with a function, accumulate it, then take its derivative, we end up back to the function. And let me show you that a little bit more just using this problem. If we start with a function, f of x equals 2x, we accumulate it. What does accumulate mean? Just what does the accumulation function mean? We're just getting the area underneath the curve, which is what we did here. All right? Then it says take the derivative of the accumulation function, x squared, and we get to 2x. So that takes us back to our function. One more time. Start with the function f of x equals 2x. Accumulate it. From the accumulation graph, you're going to get a function called the accumulation function. It's x squared. Take the derivative, you go back to 2x. So, it should lead you to believe that the accumulation function and derivatives have an inverse relationship. That is, this is all building up to the fundamental theorem of calculus, which will be examined in the next 2 chapters. Okay? So, all of this is, we're just kind of prepping ourselves for the fundamental theorem of calculus, which is, it's titled Chapter 30, but we're going to get into it in the 29th chapter as well. Okay? So, this may be a little bit blurry, but I'll try to help you kind of see it a little bit more as we go through these next examples. Okay? But here's the only thing we basically need you to know. If you take a function and you accumulate it, find all the area underneath the line from this point to that point, whatever the definite integral is, and then you take the derivative of that accumulation function, it's going to take you right back to the function. That's what I need you to know right now. All right? All right, are we seeing that a little bit? Give me a thumbs up. Okay, cool. Usually I can, see your faces in class, so it's just like, yeah, they're not getting it, or, man, they need more help, more time. Yeah. All right, so looking at this right here. Number 1, it says let f of x equal, so big F of x, okay? Let capital F of x equals the definite integral from 0 to x, f of t dt, where the graph of f of t is to the right. So here's our graph right here, f of t, all right? Now remember that f of x is the same as f of t. It's same thing, all right? To make this easier to understand, think of f of t as the rate of the snow accumulation over an 8-hour period of time For instance, at t equals 1, snow is falling at a rate of 3 inches per hour. At t equals 3, it is not snowing. At t equals 4, the snow is melting 4 inches per hour. Big F of x then represents the accumulation of snow on the ground at any point in time. Okay? So, here's what it wants us to do. Complete the table for the given times x. Okay? So, this big F of x here, it is representing our accumulation function. Okay? So, let's not freak out. This is my f of t, quote unquote, f of x, but this is my big F of x. Okay? Hey, give me 1 second. Sorry about that. All right, so looking at this right here, so this big F of x, I was looking to see. I haven't seen this in a minute. I'm calling it big F of x. I'll look up and see if there's another phrase that people use besides big F of x. I hadn't seen it in a little bit. I probably should have done that before, but I was seeing real quick if I could see something. But we'll call it big F of x now. And if the next thing, once we go to that fundamental theorem of calculus, if I look up if there's a more technical phrase to use for it, then we'll use that. Okay, but we'll just call it big F of x for now. So it represents our accumulation function. Okay, so this represents the accumulation function. Let me write this down. F of x, big F of x, is our accumulation function. There's just one M, sorry. Accumulation function, okay? And what the accumulation function is just accumulating the area. Under the line. We'd call it curve. Okay? So, big F of x is a representation of the accumulation function. And the accumulation function is it is accumulating the area under the curve. So, when you put 0, this x0, into this upper limit x here, we are going to get 0. Anytime your upper limit, lower limit's the same, it's obviously 0. There's no distance between them. All right? But how about when it is 1? So again, we're just finding the area under this from 0 to whatever the number is. So from 0 to 1, I have one square here and then a 2 by 1 triangle. So that should take me to 2. Again, that's 1 and then a 2 by 1 triangle. Base times height times a half. 2 times 1 is 2 times a half is a 1. And then that 1 plus that 1 is 2. Okay? So very similar to what we did last lesson. So 2, going to 2. Well, if I go to 2, I got 1, 2, 3, 4. And then that's 1 right there, so that represents 5. If I go to 3, well, that is 1 here, 2, 3, 4, 5. And then a 3 by 1 would give me, a 3 by 1 would be 1.5. So that 5 right here plus this 1.5 would give me 6.5. Are you guys okay? Are you guys okay with seeing me do that? Are you guys okay with sorry. Sorry. Are you guys okay with me just filling this in? Do you all understand how I'm calculating these areas? Or do I need to define that a little bit better? Do I need to draw it out? All right, Carter, you're cool. Hey, no worries, Ian. Okay, cool. All right, just making sure that I wasn't like, you're like, where in the world are these numbers coming from? All right, so when it's 4, 4 is right here. So we know that's, yeah, very good. So from 0 to 4, or from 0 to 3, we know that's 6.5. And then 0 to 4 would just take off 1.5. Or actually, it would take off 1, 2, 3, 4. 4 by 1, it'd take off 2. Okay? So 4 should be 4.5. Okay? From 0 to 5, 0 to 5, again, so that's going to take off a total of 4. So this has an area right here of 4, just based on doing the 4 by 1s. So this side is 2, this side is 2, so that's 4. 6.5, all of this minus this would be 2.5. So now from 0 to 5 is 2.5. So then 0 to 6 would be 2.5 plus, that's a half of 1. 1 by 1 is going to be a half. So then that would bump 6 up to be 3. Going to 6.5, if we go to 6.5, that just adds, if you think about this, this is 1 by half, so that would be a fourth of an area. So that would be 3.25. If we then go to 7, well, that's the same thing as that. So that takes the half back off. And if we go to 8, 8 would just simply be taking off this 1 right here. So that has an area of 1 above it. So then that would just take us back to 2. Okay, so we have seen, what we discussed on the front side was this, that the derivative of the accumulation function is equal to f of x. So since the accumulation function big F of x is equal to the accumulation function, it follows to say this right here, guys. Really important. Big F of x, or excuse me, the derivative of big F, the derivative of big F of x is equal to f of x. Now that's going exactly what we were saying on the front side. Okay, that's coming exactly from here. This is what it was on the front side. Okay, this is right here is what it is on the front side. And since this right here, we're basically saying d of dx of f, big F of x. And that's, of course, equal to big F of x. Okay? So because the accumulation function is this right here, big F of x, these two are the same, right? Up here, big F of x is the accumulation function. When we take the derivative of that, that gives us big F, the derivative of big F of x. Okay? And since we determined on the front side that this whole thing is equal to f of x, then we just simply say that big F, the derivative of big F of x is equal to f of x. Right here. Okay? So, give me a thumbs up if you're following me in that. You kind of see how that's working. Okay, again, you take a function like this right here, guys. Take a function, you accumulate it, you take the derivative of the accumulation, you go back to the function, f of x. Okay? All right. So with that idea in mind, let's complete this table right here. Okay? So let's complete this. The derivative of big F of x is equal to all of this right here. That's what I wrote up here. That's all of this up here. That's equal to f of x. So f of x is just whatever the graph is, whatever the graph of f of t is. So whatever 0 is what? 0, 1. The point, literally, 0, 1. The f of x is basically f of t. They're the same thing, remember? Up here, f of x is the same as f of t. So if the derivative of big F of x is equal to f of x, then f of x is equal to f of t. So then to complete this chart, we just need the points. So we got 0, 1, we got 1, 3, 2, 3. And again, guys, I'm pulling it from up here. 3, 0, 4, negative 4, 5, 0, 6, 1, 7, negative 1. Ooh, no, 6.5, sorry. 6.5 is 0. 7 is negative 1. 8 is negative 1. Okay. Thumbs up. Give me a thumbs up real quick. We cool there? We seeing that? We take a function, we accumulate, we find all the area of it, we take the derivative, it just goes right back to the function. Cool. All right, very good. So let's jog that memory a little bit. Remember that we can determine information for big F of x, increases and decreases, as well as relative extremia by looking at big F, the derivative of big F of x. Using the table above, make a sign chart for the derivative of big F of x and determine intervals where f increases and f decreases, and when f has a relative maximum and minimum and what those values are. Okay, so just to jog your memory a little bit, guys. Okay, so keep in mind what we're concerned with, okay, what we're concerned with here, okay, is where does it cross the x-axis? Where does it cross the x-axis? Remember when we had a function, right? And it said, it gave us this function, right? And it didn't show us the graph. We had to create the graph based on the function. And remember, we would set it equal to 0, and we had to find out where the graph equaled 0 at. So in doing that, once we figured out that, then we determined increase, decrease. All right. So we actually have that here. The graph crosses the x-axis at 3, 0, 5, 0, and 6.50 of our function. Okay? So I make a sign chart here. So I know that f prime of x is equal to f of x. So therefore, the graph of f of x would look like this. So I have endpoints at 0 and 8. And I have points at 3, 5, and 6.5. And right here, my slope will be 0. Okay? So, now, keep in mind, we already have the f of x graph. We already have that. We're basically wanting to end up graphing big F of x based on that definite integral in this graph right here. All right? So here we go. If I'm looking from 0 to 3, I'm asking myself what's happening. Okay? So from 0 to 3 on the graph, I'm saying, is it above or below the x-axis? So from 0 to 3, it's above the x-axis, so that's positive. From 3 to 5, it is below the x-axis. From 5 to 6.5, and I'm talking about this graph up here, guys, this graph right here. From 0 to 3, it's above. From 3 to 5, it's below. From 5 to 6.5, it's above. And then from 6.5 to 8, it is below. So, F increases, all right? The graph of F increases from 0 to 3, right? Comma 5 to 6.5. And it decreases from 3 to 5 and from 6.5 to 8. Sorry, that kind of got small at the end. Sorry, guys. Okay? So now, think about this graph. This is the big F, okay? This is big F of x. So when we're looking at this graph, it goes up, starts going down, changes back to up, goes back up, and then changes back to down. Okay? So that means I have a relative max at 3. All right? Now, when x is 3, what would be the y-coordinate of that when x is 3? Well, look up here at our f of x. F of x is equal to the definite integral here, right? So when x is 3, that relative maximum there, that's going to be 6.5. And I hope you're starting to see some light bulbs are starting to come off. And we also have one at 6.5 and 3.25. Because this is showing us that we're finding this function based on the area under the curve. And then we have a relative min. There's a minimum at 5, and that would be 2.5 based on our f of x chart up here. Okay, so remember, we can determine the information about concavity of big F of x by looking at the second derivative of big F of x. Since big F prime of x is equal to f of x, it follows that f prime prime of x is equal to f prime of x. So looking at the original curve, which is f of x, construct a sign chart for f prime prime of x and determine intervals where f is concave up, concave down, and inflection points. Okay? So, since f prime prime of x is equal to f prime of x, and that should make sense, we're just stepping up. Since f prime prime of x is equal to f prime of x, we just need to look at the slope. Look at the slope of f of x, which in this case is f of t. Okay, now for our sign chart, we know that we have, it ends at 8, starts at 0. Now, with concavity, the points on the graph is where the graph literally changes direction or changes slope. Okay, so at 0, this graph is starting to go up. So from 0 to 1, it's going up. So I'll say from 0 to 1, it's positive. It has a positive slope. From 1 to 2, there is no slope. So I'll say 1 to 2 is 0. Okay? From 2 all the way to 4, it's negative. From 2 to 4, it's negative. Oh, sorry. From 2 to 4, it's negative. From 4 to 6, it's positive. From 4 to 6, it's positive. From 6 to 7, it's negative, and then goes to 0 from 7 to 8. From 6 to 7, it's negative, and then goes to 0 until 8. So, knowing this sign chart, f is concave up on 0 to 1 and 4 to 6. F is concave down on 2 to 4, 6 to 7. And who could tell me where my inflection points are? What are my inflection points? Someone type that into the chat box. Very good, Morgan. 4 and 6. No worries, Carter. So, you remember inflection points are where it changes concavity from negative to positive, positive, negative. So now we can sketch the graph. Now we could have done this up here, but obviously the increase decrease kind of helps our understanding of where stuff is. It helps us to form the graph a little bit better. So 0, 1. I'm just copying these from up here, guys. 0, 1, 1, 2, 2, 5. So 0, 0. 0, 2. 2, 5. 3, 6.5. 4, 4.5. 5, 2.5. 6, 3. 7, 6.5 and 3.25. 7 and 3. 8 and 2. And then we'll just sketch it. So, this is called the accumulation function. And it's when they give you a definite integral from 0 to x, f of t, d of t. And if they were to say, find f or big F of x, find that, graph the accumulation function of this integral, this definite integral from 0 to x of f of t, d of t, this is the process. Okay? Is this flowing with you? Give me a thumbs up. Make sure you're still with me. Alex, good. All right, cool, guys. All right, last page. So, going on the last page. Let big F of x equals the definite integral from 0 to x, f of t, dt, where f is the function graph to the right. Okay? So, and this is really, it's f of x, but it's also f of t, guys. So, it consists of lines in a semicircle. Our goal is to sketch f of x. Okay? Our goal is to sketch f of x, and then obviously answer some questions about f of x. So, recall, okay? Recall simply, okay, that f, okay, f is the accumulation area. Okay? So what we're saying here is basically what is the area from 0 to 0. Okay? So just to get a start on this, this is literally what we're saying. F of 0 is equal to the definite integral from 0 to 0 of f of t. And obviously that should be equal to 0. All right? Now notice, since x is the upper limit, we're always going from left to right. Okay? So from 0 to 2. From 0 to 2. Okay? What is the area right here from 0 to 2? Well, this is if you look at this circle, this is a quarter of a circle. Well, if you know that area of a circle is pi r squared, then if you wanted to find the quarter, that's for a whole circle. If you want to find the quarter of a circle, just divide by 4. If you want to find half or a semicircle or half of one, just divide by 2. Okay, so then my radius of this circle is 2. So that's 2 squared is 4. 4 pi over 4 would be equal to pi. So f of 2 is pi. f of 4, so from 0 to 4, and again, that 4, we're putting it into this right here, okay? So big F of 4 would just be the area under this semicircle, so that would just simply be pi r squared divided by 2, and pi r squared divided by 2. Again, the radius is 2, so that would be 4 pi over 2, which would be simply 2 pi. F of 6 from 0 to 6, well, that we know that we just figured out that to be 2 pi, and that's a 2 by 2 triangle, so that would be, and it's below the x-axis, so that would be minus 2. So 2 pi minus 2. Going the other way, from 0 to negative 1. Now we're traveling to the left now. Okay, so don't forget when you go to the left, it's negative. Above the x-axis is positive. Below the x-axis is negative when you're getting the area. All right? So f of negative 1. So I'm going to the left here. From 0 to negative 1. So looking at this right here, that's a 2 by 1 triangle, which has an area of 1. Okay? This has an area of 1. But the thing is, I went to the left, so that would be negative 1. F of negative 2, that's from 0 to negative 2, so we're going to the left, and it's above, so it's positive, so we know it's going to be negative here. And then it would just simply be, we just found out that that's 1 area, and then 1, 2, so that would be 3, negative 3. F of negative 3, so from 0 to negative 3, so again, that's going left, so we just figured out that was 3. That's going to be 1, and that's going to be 1, but they kind of cancel each other out, their areas, so it'd just simply be the negative 3. I felt like I kind of went through that fast. We know that this is negative. This is 3, and then that's a 2 by 1. So that's 1, and that's a 2 by 1. So that would take us to negative 4, but then that negative would take us back. That would be plus 1, so that would take us back to that negative 3. And then f of negative 4, so from here to here, well, we know that to be... we know up to negative 3 is, we know up to from 0 to negative 3 is negative 3, so then just add on that 2 by 1. And that would just simply be 1 area. This has an area of 1 here. Since we're going from the right to the left, it's going to be negative, and since it's below, it's going to be negative, and negative is a positive. So negative 3 plus 1 would be negative 2. Any questions about those? We feel okay about all of that? Give me a thumbs up. Okay, cool. So while you're on the keyboard, someone tell me, I don't care who it is, but somebody tell me, what am I going to do to find f prime of 4? What am I going to do to find f prime of 4? All right, crickets. So keep in mind, guys, that f prime of x is equal to f of x. Yeah, very good, Morgan. Just look at the graph. Okay? Look at the graph at x equals 4, and then whatever point that is f prime of 4. So this is like really saying, yeah, very good. So this is like literally saying, what's f of 4? Well, f of 4, when x is 4, the y would be 0. So f prime of 4 is equal to 0. F prime of 2 is the same as f of 2. And f of 2 is 2. F prime of 6 is negative 2. F prime of 5, negative 1. Okay, very good. Now somebody type in, what would I have to do to find? So again, if it's asking me for f of 0, f of negative 1, I'm just finding the area from 0 to whatever that number is there. And if it asks me what's the f prime, I'm just finding the f of x, because f prime of x is equal to f of x. So I'm just looking for the xy coordinate for these points. I'm just looking for the y coordinate for each of these x's. Now coming down here to the second derivative, what do I have to look at on the graph to determine the second derivative? Yeah, concave up, concave down. Yeah, that's going to determine, that's going to show us, what it's doing. So what do I specifically need to look at on the graph of f of t, though? Look at the... Anybody in the house? Yeah, there you go, Morgan. Yeah, perfect. There you go, Ben. Look at the slope at those points. So f of 2, at 2, my slope is 0. F prime prime of 5, my slope at 5, right here. Ask yourself, what's the slope? It's going down 1, right 1. So that's negative 1. And we could, and of course this would be like saying f prime of 5, f prime of 2. F prime of negative 0.25. So negative 0.25 would be like right here on the graph. And as you see here, this line right here is going down 2 and right 1, so that should be negative 2. So f prime of negative 0.5 is equal to negative 2. And f prime prime of 0 would be, if we're looking at this, what would that be, f prime prime of 0 at that cusp? What is the derivative of a cusp? Same thing as the derivative of a corner. You should just type in 3 letters into the chat box. Very good. D and E, it does not exist there. Okay? All right. So, on what subintervals of negative 4 to 6 is f increasing and decreasing? Justify your answer. Okay? So, in order to determine increasing and decreasing, we need to know what f of x looks like. All right? So, we need to know, all right, what's our slope doing? Or excuse me, where does the when is the slope 0 determine increase decreasing? So when or where does it cross the x-axis? And since f prime of x is equal to f of x, we just look at the function and we say, where does it cross the x-axis? Well, it would cross, I can't have both actually. So it crosses at -4, -2.5, 0, and 4. So -4, 0, or excuse me, -2.5, 0, 4, and then we got 6 as an endpoint down here. So these are all 0 here. So it starts negative. It then increases from negative, So where does it cross the x-axis? And then ask yourself above or below when you're dealing with increasing, decreasing. So it's below the x-axis all the way to 2.5. From -2.5 to 0, it's above. From 0 to 4, it's above. From 4 to 6, it's below. So from 4 to -2.5, it's below it. Above it, from -2.5 all the way to 4, and then from 4 to 6, it's below it. So F increases from -2.5 to 0 and from 0 to 4. Now, the word says justify your answer. Okay, now I'm sure you're going to have to justify your answer on these two problems you're going to have to do. And your justification of your answer is that f prime of x is equal to f of x, and that is positive. Okay? And then f decreases. So we're just saying the derivative of big F of x is equal to f of x. It's positive. So it's positive when, we could say it's positive or it's above the x-axis. For decreasing, it decreases from -4 to -2.5 and from 4 to 6. And put those on here in brackets. So then same thing here. F prime of x is equal to f of x is negative. And that is the way that would work. Okay, so we found what subintervals are increasing and decreasing. We justified our answer by saying because f of x is positive and f prime of x is equal to f of x. Same thing with the negative. So it says find the absolute minimum and maximum values of x on the interval. Okay. Now keep in mind absolute minimum max. Does anybody remember what that? Can anybody recall what absolute min and max mean? Yeah, good, Morgan. It's the highest and lowest points. It's not. It doesn't have to be. It does not have to be a quote unquote maximum, a relative maximum. It's just the highest and lowest part of the graph. All right. So, F. So let's first look at. So here's what we have. Let's look at our graph. So we know the graph starts by decreasing. hits something there, then goes up, and then goes up again, and then comes down. All right. We know it starts at 4, starts at -4, ends at 6. So we need to check this minimum right here. So that would be f of -2.5. And I think we calculated that up there, did we? Oh, we did. I guess we didn't. Okay, so so what's the area under -2.5? Okay, so what is this area right here? From 0, so f of -2.5, guys. Again, when you just have the single f, it's saying what's the area from 0 to -2.5. So from 0 to -2.5, that would be 1, 2. That's 1 right there, and that would be 1. No, that's a half. So that would be a half there. Sorry. So 2 by 1 triangle right here gives me an area of 1. This right here is 2, so now I'm at 3. And then this is a 2 by half, so that's 1, and then basically half of 1 is a half. And then it's going from right to left, and it's above the x-axis, so it's negative. Because that's negative, that's positive, so it's going to be a -3.5. But go ahead and you need to look at where you see how the graph is dropping down here at 6. We want to make sure that the point here at 6 is not, since it's asking about absolute, which is the very lowest point, we see it's going down right here. Everywhere else it's going up. So right here it's going down. So we need to check that point too just to make sure it's good. So what's f of 6? And we actually calculated that up here. It's 2 pi minus 2. So that's 2 pi minus 2. And you had a calculator. 2 pi minus 2 is 4.28. So therefore, our absolute min would be is -3.5 at x equals -2.5. Okay. It asks for the maximum, so we'll do the same thing. I want to calculate. Looks like we have a maximum up here at 4. So we need to find f of 4, and we also need to find over here because it's coming up here. So let's find that f of -4. We did calculate that up here. It's -2. And then f of 4, we already calculated that too, and that was 2 pi. So my absolute max, obviously 2 pi is larger. So my absolute max is 2 pi at x equals 4. Okay. Give me a thumbs up on that. Y'all good on the past two? Feel pretty good about those? All right. A couple of you are cool. All right. Hope this is making sense. On what subintervals of -4 to 6 is f concave up and concave down? And what are the inflection points and justify your answer? So we know that the f prime prime of x, that determines concavity. It's the same as f prime of x. So we need to be looking at our slope here. We need to be looking at the slope of f of t from -4 to 6. All right? So draw this line out. I'm at negative 4, and I'm just going to start going. From negative 4 to negative 3, I'm looking at this f of t up here, up at the top right of the page. So from negative 4 to negative 3, it's going down. It's negative. From negative 3 to negative 2, it's positive. From negative 2 to negative 1, slope is 0. From negative 1 to 0, slope is negative. From 0 to 2, it's positive. From 2 to negative to 6 down here, it's negative. So therefore, f is concave up from negative 3 to negative 2, comma 0, 2. It's concave down from negative 4 to negative 3, negative 1 to 0, 2 to 6. Now, the justification for both of these is that the justification for this top one is f prime prime of x is equal to f prime of x, and that's when it is positive. For the concave down, f prime prime of x is equal to f prime of x when that is negative. And I would say f prime of x is negative. So that's our justification for both of those. We're justifying why that is the answer. And then my inflection points. Somebody tell me my inflection points. I'll give you a second. You're fine. Should be 3 of them. I would say I'm with you on one of those. Negative 3 right here, it switches. At 0, it switches. And at 2, it switches. And my justification for that is it changes from increasing to decreasing. Then, guys, we just graphed the function. We got some points up there, all those f of 0s, f of 2, f of 4, f of 6, and we just graphed this function. Yeah? Morgan, you good on that? Or you just messed up your negative 1 and 0. That was it. You had 2 of them, right? So, graphing this, 0, 0. 2 and pi, 2 and 3.14. 4 and 2 pi, which is like 6.28. F of 6 is 2 pi minus 2, which is 4.28. Going the other way, negative 1 is negative 1. Negative 2 is negative 3. Negative 3 is negative 3. And don't forget about that minimum right there, that negative 2.5. Negative 2.5 and negative 3.5. So that's what makes it dip there. And then we got our maximum. And then that last one, negative 4 and negative 2. So from -4 to 6, should be doing something like this, guys. You got a absolute minimum, absolute maximum. See how we check those endpoints just to make sure they didn't go lower? It's concave up. It's holding water from -3 to -2. Holding water here, and from 0 to 2. From 0 to 2, it's holding water. From -4 to 3, it's losing water. So we could think about that like that. From -3 to -2, it's holding water. From 2 to 6, it's losing water. From -1 to 0, it is losing water. 0 to 2, it's gaining water. And then from -2 to 1, this would be our inflection point, somewhere in here. Inflection point here as well. So somewhere in here, somewhere between -2 and 1, there's an inflection point. So I don't know where that. I'm assuming it's here, so I would assume that it would be losing there. So, questions on any of that problem, guys? Seeing no questions. Hey, I think that's it, right? Yeah, that's it for the day. So you just got the homework from there, guys. You guys got the homework from there. I will see you guys back here Thursday at 1 o'clock. Looking forward to seeing you all. If you have any questions, shoot me an email. Spend tonight while it's fresh on your mind to do the homework, or do it tomorrow or Thursday morning, whatever. So just make sure you get it done. Make sure you're keeping up. If you all don't have any questions, give me a thumbs up, and then you're free to go. Give me a thumbs up. You're good? Good. I'm glad it makes sense, Morgan. So give me a thumbs up that you're good to go, and if you're good, you guys are dismissed. Thanks so much for being here. Thanks, Ben. See you, man. See you, Alex. See you, Ian. All right, Carter. We'll see you guys. Yes, Alex. You have a good day too, man. If you have any questions, I'll be on here just for a second. So if you have any questions, I am going to mute my audio. So if you have any questions, just type it into the chat box.